Hello, everyone. Welcome to here, and thank you very much for accepting our exception to visit our UNSW 3 from our Tsinghua team. I will read the paper about the bell of Haiwang Zhong, just in case I forgot it. Professor Haiwang Zhong is currently working as a tenured associate professor at the Department of Electrical Engineering, Tsinghua University, and the director of Energy Internet Trading and Operation Research Department of Sichuan Energy Internet Research Institute, Tsinghua University. And he was granted Excellent Young Scientist funded by the Chinese National Natural Science Foundation, NSFC. He serves as the convenor of the CIGRE Working Group on assessment of system reserved and flexibility needs in power systems of the future. He was awarded the PROS SPER Net Young Scientist Award. He was awarded 5 provincial Science and Technology Awards. He won 3 gold medals in Geneva International Inventor exhibitions. His research interests include power systems operation, electrical markets, etc. And let's welcome and give the time to Professor Haiwang Zhong. Yeah.
Thanks for the introduction. Okay. Dear Professor Barron and dear Dr. Liu, it's our great honor to visit UNSW for the first time, and because based on our collaboration project initiated this year. Today, my topic is about the source grid load storage, interactive operations in new power system. And first, I would like to introduce our university and our department. Here is the Tsinghua University, which is located in Beijing, China. And it is one of the best universities in electrical engineering. And our department is Department of Electrical Engineering. The structure of our department, we call one department and 2 institutes. One department is Department of WE, which was founded in 1932. So over 90 years old department. And recently, we established 2 institutes. One was located in Beijing, and another one is located in Chengdu, Sichuan province. And these 2 institutes are focused on energy internet. This is the structure of our department. And besides that, our department owned one state key laboratory for power system operations and control, which was funded by the Ministry of Science and Technology of China. For the discipline development, we call this 1 axis and 2 wings. So it's like an eagle, the shape. So the axis is the conventional electrical engineering discipline, and the left wing was the energy internet characteristics, which shows the intersection, interdiscipline with the other subjects. For example, the information science and the material science and the thermal power and etc. And for the right wing, we called it electrification characteristics, which was the application of electrical engineering in other industry. For example, the transportation electrification, and also the chemical engineering and the other applications. So that's 1 axis, 2 wings. Also, recently we established several joint research center institute with corporations, with the major corporations in China. The first one was with SGCC, SGCRE Corporation of China. We have a joint research institute. And also for the 3 gorges, Three Gorges Corporation, and China Southern Power Grid, CSG, China Southern Power Grid Corporation of China. So this joint research institute was funded by the state-owned enterprises. So they will fund directly the research funding for the university to conduct some research projects. And also we are collaborating with Imperial College London. We have a joint research center. So we will have the annual meeting, and this year was held in London next month. So that's a collaboration mechanism between Tsinghua and Imperial College. So that's the structure of our department. And for the collaboration between Tsinghua and UNSW, we have applied for a collaboration research program, which focused on the virtual power plant, electric vehicles for decarbonization, because the decarbonization is one of the objectives of Chinese government. We would like to achieve the carbon neutrality in 2060. And for how to achieve that objective, we think that the power system will play a key role in the decarbonization. So this is our common interest between the two sides. And the picture shows Dr. Liu visited our university, who visited our group this year, right? This year. And this paper, we just published collaboration research outcomes on a journal paper, and we hoped this is the start of our collaboration, and we want to make more progress in the future. Okay, so today I'm going to talk about 4 parts in my talk. The first part is toward interactive operations. For the conventional power system, we know that the power system maintains the instantaneous power balance between the generation and the load via dispatching conventional generating units to follow the load to maintain the frequency to be the same. However, with the development of renewable energy, with more and more renewable energy integrating into the power system, the challenges arises. For the wind power integration, we know that the output of the wind power is usually negatively related to the load profile, just as shown in the figure here. And for the photovoltaic PV power, will cause the duck curve, right? So, and will bring about challenges for the operation of power system. This is the duck curve in California, United States. It looks like a duck, and however, it's becoming more and more severe these years. Now they call it canyon curve. So it's deeper, get deeper and deeper. So this will bring about the challenges for the balancing between the generation and load. For the conventional power system, we usually we dispatch the generating units to follow the load, but now we have more and more renewable energy. We cannot achieve these objectives by only dispatching the generation side. So we need to change the pattern of the power system operations toward interactive operations, which means we need to utilize the flexibility from the demand side. For example, the air conditioners or HVAC in the buildings, and also there are some flexible loads. They will vary with the price, with the electricity price in the real time. And also there are some interruptible loads which can be interrupted for a part of time, and participating in the direct load control, the program. So we need to utilize these manners to solve the problem of the balancing between the generation and load. So that's the background. We want to study to look into this problem. The second part, we would like to introduce some of the modeling analysis, how to model the problem, how to utilize the flexibility from the demand side. So here is the transition of the power system in Denmark in 1990 and in 2014. We can see a very obvious phenomenon that there are more and more distributed energy resources here. Not only the centralized power plants, but also a lot of the DG, distributed generations, with the wind power and solar. So that's the change of the power system. And all over the world, now more and more DERs integrated into the system. And these DERs, they have some kind of flexibility. For example, in the microgrid, here we have a lot of EV, PV, and energy storages. So if we can aggregate this flexibility together, so they can provide the service for their distribution network operator. And for the distribution system, if we can aggregate the flexibility here, then they can provide some service for the bulk power system operations. That's the coordination between the TSO and DSO, and also a very hot topic nowadays. And for the upper layer is the electricity trading across region. For example, in China, different provinces they are independent entities, so they can trade between each other. So if we can utilize the flexibility within the one province, then they can provide a service for their interregional power trading. So different layers. That's the method we propose to utilize the flexibility from the subsystem to provide a service for the major system. So based on this idea, we finished a project funded by the Joint Research Institute with State Grid Corporation of China. It's called the multi-layer aggregation and coordinative optimization of resources and multiple voltage levels based on feasible region projection. So that's the basic idea of the feasible region projection, is that we want to depict the dispatchable region of all the DERs within the subsystem to form a feasible region, like here, a feasible region. It is a high-dimensional problem. We want to project to a low-dimensional space. This is the basic idea, so it's called a feasible region projection. Because for the power system, it's naturally a multi-layer problem. So we can aggregate the flexibility from the lower layer to provide the service for the upper layer. And for this, we have two papers. If you are interested, you can scan the QR code, but it's in Chinese. Sorry. But we introduced the basic idea for this method. So this is the mathematical formulation. We want to characterize the problem between the coordination of the TSO and DSO. So for each DSO, it's a subsystem, subproblem. The first idea is we can optimize together with a joint optimization. We obtained all the information from the DSOs and to calculate the joint optimization, but it's too complicated. And sometimes it's infeasible because the administration problem, they are organized by different entities. So the solution we propose is to decompose the problem into several sub-problems, and the major problem, the two-layer coordination between the TSO and DSO. But the problem is how to describe the feasible region of the DSO. So here is the idea, is the equivalent projection, feasible region projection. For each subsystem, we have some internal variables. We want to delete these internal variables to only maintain the interface variables, coordination variables. And then these are low dimensional, and these are high dimensional for the internal system. And then we can project all the internal constraints and variables to the interface between the subsystem and the major system to form the feasible region phi. That's the illustration of this process. And if each DSO can calculate their feasible region, this is the first stage. And then the second stage is the optimization of the TSO. They collect all the feasible region as the constraints to form the upper layer problem to optimize, and then obtain the exchanged power or the price signals between these two layers, and then iterate for one time. Then the optimal solution will be obtained. This solution will satisfy all the constraints within each subsystems, because when you calculate the feasible region, you consider all the internal constraints and variables in each subsystem. So this is the result will be equivalent to the joint optimization to do the calculation together, and no iteration is required. So this work, we published a two-part paper on attribute transactions on power systems to introduce the idea and the methodology we proposed. And this is the detail of the calculation method. So for the distribution network system, we need to consider the AC power flow, but it's nonlinear and non-convex problem. It's very complicated. So for the first step, we linearize the problem. So with linearization, the feasible region phi becomes a polytope. We use the iteration algorithm to find the vertex of the feasible region, and then to expand the feasible region to find more vertices. And if we find enough vertices, we can calculate a high accuracy feasible region of the subsystem. And this is the second step to solve the linear projection problem. However, this is our linearized problem. So the last step is to recover to the AC power flow, AC solution to recover the feasibility within the AC framework. So what is the application of this methodology? We think the first scenario is for the virtual power plant, because for the conventional power plant generator, we know that we have the PQ curve, which is the feasible region of a generator, like right the power, active power and reactive power. You have the D curve. For the virtual power plant, we hope it will act just like a conventional generating unit. So we want to formulate like the PQ plan. If we can characterize the feasible region of a virtual power plant, then for the dispatch center, I can just view the virtual power plant as a conventional power plant. We can dispatch the active power and reactive power of the VPP. So that's the application scenario of the feasible region projection method. Here's the mathematical formulation. We use the AC power flow constraints, so we can calculate the feasible region here, interface variables P and Q. So this is the internal system of the virtual power plant. We consider the constraints and the characteristics of the DG, and so we formulate the feasible region of the VPP, and then they can act just like a conventional generating unit in the power system operations here. So that's the first application of the methodology. The second one is we can utilize the flexibility from the demand side to secure the bulk power system operations. We can show it in the animation here. For example, we can use the feasible region projection methodology to aggregate the flexibility from the demand side, from the multi-layer. We aggregate from the microgrid to the distribution network, from the distribution network to the bulk power system, the transformer, right? And then we can obtain the feasible region here. This feasible region is just like a conventional generating unit from the perspective of the dispatch center in the bulk power system. The first scenario is the renewable energy. For example, there is a sudden drop of wind power output. We assume that at that time, all the conventional generating units has been dispatched to the maximum power output. So in that case, we have no other measures to encounter the problem. So we can change the operating point of the feasible region from the demand side. So we can change the operating point here to recover the frequency to 50 hertz or 60 hertz, the normal state. Just the first, for example, we can decrease the electricity consumption for the air conditioner, or we can discharge the energy storage system. And for the second scenario, because our transmission lines are exposed to the natural environment, so sometimes there will be accidents, contingency, so the outage of the transmission lines. Then the power flow across the transmission line will be transferred to the other transmission lines to cause congestion of the other transmission lines. And in this case, we need to adjust the output of the generating unit, and also we can adjust the operating point from the demand side to eliminate the congestion of the transmission system. And the third application is for the integrated energy system or the multiple energy system, because nowadays the coupling between the electricity network and the heating networks and the natural gas networks and also the transportation networks are more and more coupling together. So sometimes when the electricity networks encounters the challenges for the balancing, we can ask help for the other systems. Here, for example, we use the feasible region projection method to describe the feasibility between different energy forms. For example, this here. Oh, yeah, here. Yeah, this is the for between the electricity, the gas, and heating networks. So this describes the feasibility or feasible region between different forms of energy, which means that we can, for example, we can switch from electricity to natural gas when the electricity price is extremely high or there are not enough electricity supply during the peak hours. So we can use the flexibility in the integrated energy system to improve the security and reliability of the whole energy system. Here is also another papers to introduce the basic idea. And the fourth application is to support the nationwide electricity market in China. In the past 9 years, dated back to 2015, there was a new round of electricity market reform in China to establish the spot electricity market, based on the LMP, locational marginal price. And now there are 3 provinces has going to the formal running of the spot electricity market, which is Shanxi province, Guangdong province, and Shandong province. So these 3 provinces are now running daily day-ahead market and real-time market to form the locational marginal price, and the settlement of the electricity trading are based on the LMP. So that's the electricity market. For the national objective of the electricity market, we hope to establish a nationwide electricity market. For example, from the bottom, this is the local electricity market within a microgrid or in the distribution network system. And this part is for the provincial or regional across different provinces, this layer electricity market. So that's the major part of the electricity market in China nowadays. And for the upper layer is the cross-regional, because China is divided into the six regional electricity network. So between different regional electricity network, there are some exchange power together. So for this scenario, we can also use the feasible region projection method to describe the feasible region of each province, for each province or each regional electricity network. And then we only consider the Thailand power, the Thailand exchanged power. We can use this method to describe the feasible region for the power trading between different regions. So that's another scenario we can apply to. So here is the feasible region for the Thailand exchange power. So we can use this for the power exchange. So they can organize the electricity trading within the feasible region. Then they can be applied in the dispatch center. So that's the fourth applications. So that's the second part, is the modeling analysis. If we want to utilize the flexibility from the demand side, we need to conduct some aggregation. And the third part I would like to introduce is the solution algorithm and focus on the combinatorial optimization. It's a MIG problem. In conventional power system, we know that there's a very classical unit commitment problem, which is to decide the on-off state of each generating unit across a day. So it is a large-scale 0-1 binary mixed integer programming MIG problem. If we further consider the source load grid storage interactive operation, and this challenge will be even more. And for the mathematical problem, it's we usually use the branch and bound algorithm to decide the 0 or 1 state, right? So it's a very large-scaled branch and bound tree. So usually we will encounter the dimension curves. It's a very difficult problem in power system optimization. So in order to solve the problem, we try several aspects. The first is from the modeling aspect. We are looking into the load profile of the problem. This is the load profile here. We can find that in some periods, during some periods, the change of the load profile is small. And in some periods, the change are greater, right? So we ask the question is that whether we can aggregate the time period to use only one decision variable to represent the on-off state of the generating unit. Based on the basic idea, we propose an index to describe how to aggregate the time periods. It's the challenge. It's the challenge to the net load. We define an index, and based on this index, we use a dynamic programming method to find the optimal aggregation results based on this. And after these calculations, we can simplify the model to reduce the number of the 0-1 binary variables. So if we use this model, we relied on the commercial MIP solvers. The calculation algorithm efficiency will be improved. That's the first job we have done. And the second key technique is we introduce the induction function, which means in our objective function, sometimes we have the same generating units with the same cost function. So for these generating units, they will bring about the problem in the commercial solver to decrease the efficiency of the solution. So we want to solve the problem. We want to utilize the solution of the root relaxed problem, because in the root relaxed problem, we also will have the solution of the 0-1 binary variables. For example, 0.9 or 0.1, they are not 0 and neither 1. But the relaxed solution also has some physical meaning, which means this generating unit tends to be on or tend to be off. So we utilize this tendency information to construct an additional part in the objective function, which we define induction function, to add to the original objective function to induce the searching of the branch and bound algorithm. So the effect of the induction function is we can increase the pruning process of the branch and bound solution. For example, we can cut this branch, and we can cut this branch to find the optimal solution more efficiently to position the optimal solution. So in that case, we can increase the searching efficiency based on the induction function. And the third technique we propose is the relaxed neighborhood searching, which means during the branch and bound solution searching, sometimes we will find a relaxed optimal solution, which means this is not a feasible solution because some of the binary variables are not binary. They are located between 0 and 1. But however, we can limit the searching space surrounding the optimal relaxed solution. So we can reduce the size of the searching. This is a small system example. Originally, we need to enumerate each point here. If we utilize the neighborhood searching, we can only search the red part, the red spot here. So it's 64 versus 16. So the efficiency of the searching will be improved further. And the fourth technique is for the effective constraints identification. which means we want to simplify. Also, we want to simplify the modeling, because in the optimization problem, there are many constraints in power system optimization, especially for the transmission line power flow constraints. There are a bunch of that. We want to identify which is redundant constraints and which are the non-binding constraints. These are two types of invalid constraints. For the redundant constraints, which means that these constraints will never be violated. For example, the constraint 5 and constraint 6 here, they will never be binding, so we can delete it to simplify the model. And the second type is non-binding constraints, which means these constraints are far away from the optimal solution. For example, these two constraints, they are not binding at the optimal solution here. So we can also delete these two parts, these two constraints will not affect the optimal solution. After this process, we can eliminate some of the constraints to simplify the model. And based on this research, we participate in an IEEE task force for solving large-scale optimization problems in electricity market and power system applications. And this is we finished a white paper and also submit a paper to the IEEE transaction and power systems. This is the accepted paper here. And this is a technical report. Technical report was awarded the outstanding technical report in IEEE PES here. And also we didn't stop at the academic research. We applied these methodology to form a software, and has been applied in 10 plus provincial control centers in China, and also in Guangdong electricity market clearing algorithm was also supported by our group to support the spot market as the key market clearing algorithm, the security constraint unit commitment and security constraint economic dispatch. That's the third part, and the fourth part is also the characteristics of our group, because our group, we not only focus on the technology problem, we also focus on the policy and also electricity market mechanism design. So the last part I would like to introduce is the mechanism design problem. Here is the animation is to introduce the transition of the operation pattern from the conventional mode is we dispatch the conventional generating unit to follow the load, because we assume that the load is inelastic. They are fixed load. So in that case, when the renewable energy fluctuates, the change of the thermal power plant is unavoidable. So the conventional thermal power plants follow the fluctuation of the renewable energy, just like this. Renewable fluctuation, and then the thermal power plant change its output to follow the fluctuation. However, for the new power system, we can change the pattern because we have a lot of IoT application. We have the real-time electricity price. So when the fluctuation of a renewable happens, we can transit this message toward the demand side. So the demand side flexibility can be incentivized to follow the generation. In that case, the thermal power plant can change little because the efficiency of thermal power plant will change if you reduce the output of the thermal power plant. The efficiency will also go down. We would like to maintain the thermal power plant to be a high efficient operating point for most of the time. so we can utilize the flexibility from the demand side. And the first mechanism we propose is that we want to improve the electricity price signals. We call it the LMP with overall cost. Because in the conventional pricing mechanism for the LMP, we have three components. The first is the marginal cost for the generating cost and the congestion cost due to the transmission line congestion. And the third part is the transmission losses, three components to form together the locational marginal price. And this concept has been applied all over the world. This is in the United States, Texas, the spatial distribution of the LMPs in Texas, and also in PJM, and also in New Zealand. A lot of countries are utilizing the LMP concepts. However, in conventional price signals, the transmission costs are not included, which means that the impact of the transmission fees are not included in the LMP signals. So we would like to improve the LMP concept to include the transmission cost, because transmission cost is a major part of the electricity price. So we want to consider the transmission cost here to form an LMP with overall cost here. That's the basic idea. But how to realize this objective? First, we identify the effective transmission cost, because sometimes in China, the investment of the transmission lines, they are more than we really need it. So here is an example for the blue curve. For the blue curve, are the normal condition, the power flow, the power transmitted across the transmission line. So this capacity are valid. We really need it. And the second part is the capacity reserved for contingencies, just like the example I showed it previously, right? So when there is some contingency, the transfer of the power flow, so we need to reserve the capacity to prepare for that. And this capacity are also valid. The third part is the capacity reserved for future need, because the construction, the building of the transmission lines will take a long time compared with the generating unit, especially the renewable power plants. It's very fast, we can build it. But for the transmission line, it's very slow. So we need to prepare for the future need. So this part we can also calculate it identify it as an effective capacity. However, the last part, we can identify invalid capacity. Otherwise, there will be an AJ effect in economics, which means for the regulatory industry, there is a wrong incentive signal to encourage them to invest more. So this method we propose is we identify which are the effective capacity. Then this capacity can go into the transmission tariff, but the invalid capacity cannot go into the transmission tariff. That's the first work we have done to identify the effective transmission cost based on the structural function of the capacity of the transmission line. And the second part is we want to allocate the transmission cost during the year. That's the temporal allocation of the cost. In this problem, we reorganize the load profile. For example, we assume that this is the year, the power flow curve of a whole year. We reorganize it to sort we put the highest power flow on the left and the smallest on the right. We form a continuous continuous, low duration curve. And when we form the duration curve, we can allocate the transmission cost corresponding to different capacity, to different load levels here. So we can allocate to different different load levels here. So this method, the basic idea is to consider the utilization rate of different capacity. For example, for the base load, the utilization rate is very high, but for the peak load, the utilization rate is really small. So when we allocate the transmission cost into different levels of the capacity, and different color means different price. It will be more expensive in the peak capacity and cheaper at the base load. And this is the first step. We reorganize the load profile, and we allocate the cost corresponding to different structure of the transmission lines to different load. And then the second is we recover the tiered pricing from continuous, the low duration curve, back up to the time sequential power flow curve, which is like this. We recover to the time sequential curve, and then we can obtain the time variant transmission cost, transmission price here. So we can add the different price signals together to form the price signal for each time period here. So that's the temporal allocation. That's not enough. This only solves the problem how to allocate the total cost into different time periods. And the second job is to allocate the spatial, because it's the LMP, it's locational marginal price. So the second work we have done is to optimize the spatial allocation of the transmission cost. Here we use the power flow tracing method. We calculate the power flow of the system, and then we allocate the transmission cost just along with the path of the power flow. So from the generation side to the load side, and then for each location, we can have a transmission cost component. This component can be added to the conventional LMP. Then we form the LMP with the overall cost. And this is a paper on the applied energy. We introduced the transmission cost allocation method and utilize for the planning problem. And the second mechanism we propose is for the energy sharing, because the sharing economy has been applied in different areas, like I saw the Hello Ride, the bicycle sharing, right? And for the power system, we have the power grid. So the power grid is acting as a natural platform for the energy sharing because they connect everybody together. So we can apply the ideas of the energy of the sharing economy in the energy sector. Here is what we propose. For example, we have some vacant DERs here. When you travel or you are not at home, then the PV, your rooftop PV, can generate electricity and sell to your neighborhood. But this, we need to design the mechanism very carefully to recognize the contribution of each person and to allocate the creative value to everybody. So on this part, we propose the application of the sharing economy in energy markets to accurately identify the external value and cost and allocate the value, the added value to the appropriate participants to encourage more people to join the energy sharing. And this is our book published last year, I think, to introduce the basic idea of the energy sharing in electricity market. Okay, so that's the 4 parts I would like to introduce in this talk. So we can see that the new power system with a high penetration of renewable energy is not only the innovation of technology, but also the mechanism. We have to design the mechanism carefully to incentivize more customers will participate in the power system operations. And the energy system will be reshaped by renewables, flexible loads, and energy storage, forming a new form of source-grid-load storage interaction and creating an open, shared, competitive, and win-win energy ecosystem with energy internet technology and a fair value distribution mechanism. That's very important to recognize the contribution of each participant accurately to incentivize them to join together. Okay, that's all. This is my email. And these 2 QR codes are, one is the ResearchGate of my ResearchGate website, and the other one was a WeChat QR code, which was operated by myself to introduce some of the some papers and some recruiting advisement for the PhD and postdoc, and has some. Now it's I think it's impactful in the academia society. Okay, that's all. Thank you. Thank you. Is there any questions?
Thank you. That was brilliant, Haiwang. I really enjoyed the talk, and there are a lot of similarities, and I would love to share also what our group's doing in the next hour or so. I have 2 questions. One is more about China's power system and how it is different than where you are now in Australia. So in particular, in Australia, we have lots of distributed rooftop solar systems. It's now over 25 gigawatts. I mean, it's for Australia's power system, it's quite significant. Over 40% of households, freestanding households, have these systems. And our utility scale solar is lagging a little bit behind, so we have a really big distributed solar problem. How it is in China at the moment in terms of utility scale solar versus distributed? And something related to this, due to the population of China, I would imagine the electricity consumption would be very significant. So do distributed energy systems cause any disturbance like the duck curve you've shown in California or in Australia? Is that a problem for you at all, or maybe in the next 10, 20, 30 years? What are your thoughts? So that's my first question. Maybe let's start with that one. Yeah.
Okay, thank you. Nowadays in China, the distributed PV is developing very, very fast, especially in the northern part of China. Because in southern part of China, it's rainy. The sunshine is not very resource is not very good. But for the northern part of China, the sunshine resources is very good. So, for example, in Shandong province and Hebei province, there are many distributed PVs, even more than the utility scale PV station. So they have already made some problems to the power system operations. For example, the transformer. In the previous day, the transformer usually transmit the power from the bulk power system to the distribution network. Nowadays, some of the transformers are vacant, no power transmit from the bulk power system to the distribution level. And even some of them are reversed, the power flow reversed to the bulk power system. That's one of the problem. And the second is for the voltage. Because at the end of the distribution network, you have a lot of DG injection power to the network. So we'll increase the voltage at the end of the distribution network. So sometimes the voltage will exceed the limit of the standard operating standard. So that's I think it's not a future story. It's now happening nowadays in China. So for the State Grid Corporation of China, SGCC, I think the fluctuation of the PV, including the utility scale and the DGE, are 0.24 billion watt. How to translate? It's 0.24. No. Because the how to say the gigawatt, not gigawatt. 2.4亿千瓦，2.4亿千瓦是多少？ So it's very huge. The change of the PV, especially after the sunset. After the sunset, the drop of the PV has caused a very severe problem for the balancing between the generation and load. So which means you need to have a large capacity of the thermal power plant to acting as the backup for the PV. It's very huge, very, very huge. Yeah. So that's the biggest concern of the power system in China. How to balance between the generation and the load.
Yeah, great. Thank you. That's very helpful. My second question is about some of your methods that you described around optimizing a large number of smaller units versus you've decided to group them together and simplify this problem and created subgroups and then lots of interesting methods there. Within this optimization ecosystem, how are you taking uncertainty into account? Uncertainty in terms of renewable energy generation, in terms of prices, in terms of lots of consumption from the load side of things. And the uncertainty of the forecasting, is it first how are you taking into account the challenges with forecasting different things, and are you looking only day ahead, or are you looking in weeks, months, years? Is that more planning, or is it more short-term operation? So that's the second question.
Okay. Yes, the uncertainty is a big issue in the power system operation in China now. Especially with the penetration of the renewable energy increase a lot compared with the conventional power system. So nowadays, for the power system operation, they will make a week ahead scheduling to get prepared for the extreme weather. For example, the heat wave to sustain for 3 days, last for 3 days or a week. Or the cold wave to last for 3 days or 1 week. So they have a week ahead schedule getting ready for the extreme weather. And they have a 3-day ahead schedule to make sure they have enough adequacy. They have the generation adequacy to maintain the balance between the generation and load. And for the spot market, it's day ahead. It's day ahead market clearing every day. They also have the real-time market, which is about 15 minutes to 30 minutes ahead. So to clear the markets on the real-time scale. And also they have the emergency dispatch, which means they are not market-based. You dispatch first, and then you settle later. So you solve the problem first, and then you consider the cost of that solution. So they have the emergency dispatch mechanism in China. So you can forget about the market. So on the normal condition, they are market-based. You dispatch the generation based on the market clearing result. And there's a very special mechanism designed in China now. Is we call some of the electricity are still based on the not market-based. So we have two parts of electricity. Some of them are market-based, and some of them are plan-based, which means it was decided by the government. For example, in China, most of the hydro power plants was located in the southwest of China. So the electricity generated by the hydro power plants are transmitted to the east part of China. So these, from the west to the east, electricity transmission, usually the decisions are made by the government. So they decide how much electricity transmit from the west to the east. So these boundary conditions you cannot change. And based on this, under this framework, you can optimize each province given the boundary condition here. So they are, it's a very that's why the electricity market is very complicated in China. We need to consider different components, composition of the electricity in the power system. Yeah. Thank you, Professor Bear. Hi, Professor.
Thanks, Professor Zhong, for the nice talk. I'm not in this research field, but I just have probably a naive question. So you can do a lot of simulation work to make the grid system operating well. My question is, how about cost? When you want to build this kind of grid system, will that have very high cost? For example, I see there is an example you make when there is a sudden wind power drop. You have a kind of solution to make the output match the consumption, but that means you will have to have a storage system, like energy storage to discharge to supply to the users. Will that increase a lot of the cost for the whole system, the grid upgrade when you want to build such system?
Okay, that's a very good question. It's the economic, right? It's the cost of the solution. Yes, actually, the cost of the energy storage technology is relatively high nowadays, especially for the battery and pump hydro. Pump hydro is the majority of the energy storage in power system because it's the utility scale, very large scale pump hydro. But compare with installing the peaker generating unit, because usually the challenge is happening during the peak load hour. If you install a generating unit to solve the problem of the peaking hours, the utilization rate of the generating unit is very low. For example, for a year, only 200 hours or 300 hours, then you cannot recover your investment for the peaker unit. So for the solution we propose, we utilize the flexibility from the demand side. For example, for this building, we just turn off the air conditioner for 15 minutes. That will count. That will help the power system to solve the peaking hour, the problem. So it's Compared with installing the peaker unit, it will be more economic to utilize the flexibility from the demand side. However, you still have some adding cost because you have to install the communication and control, right? So, but these are the IT. Usually, they are IT infrastructure. Nowadays in China, these IT infrastructure are usually they are already there. So you just what you need to do is you design a mechanism to incentivize the customers to participate in the program. That's the key problem. In fact, the technology is not a problem. The key problem is the mechanism, the signal, right? Thank you. Thank you.
Hi, President. I'm particularly interested, thanks for the talk. I'm particularly interested in how is the high-dimensional solution space being projected into lower dimensional solution space. I'm interested in that because when I went to your group, I introduced my module. My module have like perhaps 5 to 6 dimensions. For our algorithm, it takes less than 200 iterations to solve, but it's getting slower and slower when the dimension is getting higher. So my question is, I just wanted to get to know more about how was the high-dimensional problems being projected into a lower dimensional solution space to sort of speed up the speed to find to converge to the minimum objective functions. I would like to know more about it, so see if that's some technique I could apply to my research as well.
Okay, thank you. Yeah, that's a very good question, is how to realize the projection from the high dimensional space to the low dimensional space. The mathematical formulation, in fact, is the elimination of the variables you are not concerned with. So you do the elimination calculation. For example, the Gaussian elimination. So you delete some of the elements in the matrix. So and then you combine or you remain only the variables you are concerned with, the coordination variables. I can send you some papers for your reference. We have in fact there's a animation here is we find the vertices. Here, this part. Yeah. So it depends on your mathematical formulation. So this is just a simple illustration of the algorithm, how to search for the vertex and then to expand your boundary to find another vertexes, and then to form the feasible region. Finally, so that's a simple illustration. We have a corresponding mathematical algorithm to realize this effect. Yeah. The basic idea is to eliminate the y variables here. We eliminate yr variables here. We only remain the coordination variables you are concerned with.
Yeah, thanks for that. I think that's quite helpful. So that's based on like penalty, right? Like how you guide the algorithm to expand the shape.
It's not based on the penalty function. It's based on the you determine the expansion direction and then to push the boundary outward to find another vertex. It's not based on the penalty, I think.
Okay. All right. I'll look at the paper for more details.
Okay,
Thanks.
Thank you.
Thank you, Professor Zhong. I have a question about the non-iterative solution here. How to realize the non-iterative? Just the one step is okay?
Yes. The non-iterative is that because for each subsystem, when they calculate their feasible region, they have considered all the internal constraints And so the obtained feasible region can represent all the constraints within the subsystem. So when the upper layer problem, to solve the upper layer optimization based on the boundary condition submitted by each subsystem, they can realize that the solution can satisfy when they transmit the solution back to the subsystem, they can satisfy all the internal constraints of the subsystem. So that's we don't need to iterate between these two layers.
So we just communicate one
time. Yeah. Yes. The idea we want to realize this is because in the realistic practice of the power system operations, the time is very limited. If you iterate together, you iterate one and one again, and the time is not enough. So they will prefer only exchange information for one time, and then because they have other procedure, for example, the security check, and they to check the price signal or their load forecasting. So they have a lot of other jobs. So the time left for the coordination is quite limited. So they don't like the iteration.
Yeah.
Yes.
Okay, I will read the paper for more details. Thank you.
Okay, thank you.
Yeah, I would like to go a little bit further after Kevin's question. Can we go to page 18?
18?
Yeah. Yeah, I just wonder, for example, if there is a sudden drop for the generation, we need to do some action from the demand side to follow the generation. So who should be responsible for the control of demand side?
Yes, that's a very great question. Usually, the control of the whole power system is the dispatch center, the control center. But usually, they will not control the DER directly. So there's an intermediate layer, for example, the VPP. So the VPP is the entity which can receive the signal from the control center and then to control all the DERs aggregated by the VPP. So that's a three layer: the control center, the VPP, or the load serving entity, and then the DERs. Usually it's this layer. Yeah.
Is there any real-world application for this mechanism in China?
Yes. For example, in Jiangsu province, they have the source grid load interaction pilot project. Is when there are contingency happens, they can control the load to cut the load. For example, several hundred megawatt load at a very small time scale, very fast. They can cut in millisecond. They have built such a control system, the software and the hardware, and they have signed they have negotiated with the customers, which can let them to control the load. So they collect a lot of interruptible load, so they can control directly, very fast. And also, like in Shanghai, they have a lot of commercial building. So the HVAC system, they have built a virtual power plant to collect all the information from the HVAC system, and then there's a virtual power plant software platform can control the building. And for Shenzhen Power Dispatch Center, they also build a VPP platform, so they can control for example, the EV charger, EV charging station, because now the taxi in Shenzhen are all electrified, all EVs, the taxi in Shenzhen. So they have a lot of centralized the charging station. They can control the charge and discharge of the station.
Thank you. And so it means that it's mainly focused on medium scale or large scale. It's not for individual residential one. It's the industrial or commercial one.
Usually are CNI customers because they are more, the scale are larger. Yeah.
Thank you.
Thank you.
Any question? No? Great, thank you. Thank you very much.